Welcome everybody. In this video, we're going to take a look at the 2018 FRQs, specifically numbers 1 through 3. So let's go ahead and get started with number 1. So this is a calculator active question, so make sure you use the graphing calculator to help you out here. So for number 1, it says people enter line for an escalator at a rate modeled by the given function, or modeled by the function r given by that function, where r of t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. There are 20 people in line at t equals 0. All right, so just to kind of get a feel for where we're at, it's important that you recognize that this is a rate, right? R of t represents a rate. There is another rate given to us of people exiting the line at that constant rate. And then we also know that there are 20 people in line at time t equals 0. All of those are going to be important pieces of information at certain parts of this problem. So let's just take a look at part A. Part A says how many people enter the line for the escalator during the time interval t greater than or equal to 0, less than or equal to 300. So we were given that r was the rate at which people enter the line. And what we need to remember is that if we integrate a rate, we get the amount of change. So what we're going to do for part A is we are going to set up the integral from 0 to 300 of r of t dt. And because this is a calculator active question, we are going to use the calculator to find that integral. So if we go ahead and set that up, we have the integral from 0 to 300. And let's see, we have 44 times, in parentheses, t divided by 100, and that quantity is cubed. And we are multiplying by 1 minus t divided by 300, and that quantity is being taken to the 7th power. And we're going to do that with respect to t. And if we hit enter, we should get the answer of 270. All right, so that answers part A. 270 people entered the line from 0 to 300 seconds. All right, so part B. During the time interval, t greater than or equal to 0, less than or equal to 300, there are always people in line for the escalator. How many people are in line at t equals 300? All right, so let's just try to think about what we know. R of t is the rate at which people get in the line. They exit the line at this constant rate of 0.7, and there are 20 people in line initially. So based on that, the amount of people in line at any given time can be found by the initial amount of people in line, which is 20, plus the amount of people that get in line, which is going to be measured from 0 to x of r of t, and then minus, and this should have been a t by the way, and then minus the rate at which people get out of the line from 0 to t, which is given by that constant function of 0.7. So, I mean, that right there could be the expression to model this situation. We want to know how many people are in line at 300 seconds, so we'll evaluate that integral when t is equal to 300. So we have 20 plus the integral from 0 to 300 r of t dt minus the integral from 0 to 300 of 0.7 dt. Now, some of these values we already know. All right, we know that's 20. We found that this is 270. And then really all we need to do is integrate this which you can use the calculator, but the integral of 0.7 is going to be 0.7 t, and we're evaluating that from 0 to 300. So if you put that all into your calculator, you've got 20 plus 270, and then this is going to end up being, was that 210. So 290 minus 210 is 80, which means that at t equals 300 seconds, there are 80 people in line. Oops. All right, so looking at part C now, it says for t greater than 300, what is the first time t that there are no people in line for the escalator? Well, we know that at 300 seconds, there are 80 people in line. So it's going to be 80 minus. We know that at 300 seconds, nobody is getting on, or nobody is getting in line for the escalator because you have 0 for the rate at which people are getting in line. So we are going to subtract the rate at which people are getting out of the line, which is still going to use that constant rate. So we have the integral from 0 to 300t of 0.7 dt. And I guess technically this probably should be dx if we're going to use t as that upper limit there. So what we have, and we want that, to equal 0, because we have 80, and then when the people get out of line, we want that to be 0. So if we solve this, we have 80 minus 0.7 x, technically, and we're evaluating that from 300 to t, and we want that to equal 0. So if we set that up, we've got 80 minus, and then you've got 0.7 t minus 0.7 times 300 equals 0. All right, let's see. We can kind of solve all this out. This is going to be minus 210 equals 0. And if we combine, we've got 80 minus 210. So what's that going to be? Negative 130. So if we add 130 to the other side, we should be able to solve for our answer. Let's see. Oh, this would have become a plus because you're subtracting that value. This is actually equal, was that 290? So we're going to subtract 290, and we divide to find our t value. And if we do negative 290 divided by negative 0.7, we get about 414.286 seconds. So about 414.286 seconds. And that would be the answer for part C. Now, if we take a look at part D, all right, D wants us to find for t greater than or equal to 0, less than or equal to 300, at what time t is the number of people in line a minimum. All right, so right minimum, we want to know absolute minimum in this case. So we need endpoints and critical values. It says to the nearest whole number, find the number of people in line at this time, justify your answer. So we know that our endpoints are 0 and 300. But we need to find the critical values, which are going to come from the derivative. So we need the rate at which people are getting in line minus the rate at which people are getting out of the line to equal 0, which is another way of saying we need R of t to equal 0. Okay, we need the rate of people getting in line to be equal to the rate of people getting out of line. So that's what we need to find. So we can use our calculator to solve that equation right there. So let's see if we pull up our calculator now. I would have been smart to store this function in the calculator. I did not do that, so I'm going to have to go from the beginning, but we're going to go ahead and do algebra. We're going to solve, and we want this function 44 times t divided by 100 to the third power times, and then in parentheses, 1 minus t divided by 300 to the 7th power. We want that to be equal to, let's see, 0.7, and we're solving for the variable t. So if we hit enter, we should get some answers, and it looks like we have two possibilities for critical values. So we've got 33.01330 and 166.57472. So we have our critical values. Our t equals, let's see, it was 33.013, what were the other decimals? 30. And 166.57472. Now, those become the critical values that are in our interval. So now what we need to do is we need to basically find the number of people in line at the endpoints, which is 0 and 300, and then also at the critical values, which is 33.01330 and 166.57472. Some of these we have already found. So you don't need to do the work twice. I mean, we were given that at time t equals 0, there's 20 people in line. So you've got 20 people in line at this point. And in part B, we found out how many people were in line when t was 300. So we have those two values. What we need to now do is find the other two values, which again are going to use this function right up here. So we're going to go ahead and do that on our calculator. All right, so we had 20 plus the integral from 0 to 33.01330. And as you can see, I would have been smart to save that function because I need it again. All right, but we're going to then multiply that by 40, or take the integral of 44 times t divided by 100 to the third power times 1 minus t divided by 300 to the 7th power. That is with respect to t. And then we have to subtract, whoops, that did not come out the way I wanted to. Get out of that. We're going to subtract the integral, so shift plus, from 0 to that same time, 33.01330 of 0.7 dt. Hit enter, and we find out that there's about 3.803 people in line at that time. So if you go back to your chart, this is now approximately 3.803. And then if we go back to our calculator, we got to do this one more time. So if I come up here and I highlight that, I should be able to get that function back here. And now all I need to do is change that upper limit on my integrals to 166.574, and what was it? I think it was 72. And then I need to just make sure that I do that on the other integral as well. So 166.57472. Let's get rid of that last decimal. Hit enter, and it's about 158.070 people. So 158.070. All right, so those are the possible answers. So in this case, whoops, we were looking for, to the nearest whole number, find the number of people in line at this time, and we want the minimum, okay? And basically what we have is there is a minimum of 4 people in line when t equals 33.013. And that would answer that question. All right, guys, that does it for question 1. Make sure you keep watching and check out question 2. All right, so if we just kind of move on to question 2, let's see what it says. Again, question 2 is another calculator active question. So here it says a particle moves along the x-axis with velocity given by v of t, which is equal to 10 sine of 0.4 t squared over t squared minus t plus 3 for time t greater than or equal to 0, less than or equal to 3.5. And the particle is at position x equals -5 when t equals 0. All right, so obviously it is important that we recognize that we are given a velocity function, right? We are given a specific time interval for which that applies, and we're given a starting position or initial position of x equals -5. So what we want to do here is for part A is to find the acceleration of the particle at t equals 3. So if we're doing part A, the acceleration is going to be the integral of velocity. So that's what we're going to have to do, is we're going to have to take the integral of velocity at t equals 3. Okay, so we want the integral of velocity at t equals 3. No, I just did that completely back up. Okay, I'm getting myself all mixed up here. Velocity is the integral of acceleration. Acceleration is the derivative of velocity when t equals 3. So the acceleration, a of t, is going to be the derivative of velocity. All right, and we want to know what a of 3 is, which is the derivative of velocity evaluated at 3. All right, so let's be a little bit smarter about how we use our calculator this time. What I'm going to do first is I'm going to store v of t in my calculator. So remember, to do that, you can give the function its name, and then you're going to go control and get this colon equals, and then we can type in our function. So let's make sure I get this typed in correctly. We have 10 times sine of 0.4 times t squared, and we're going to divide all of that. So again, I probably should have done parentheses. So we're going to divide all of that by the function t squared minus t plus 3. Hit enter. All right, and when it's stored properly, it should say done. Now, what we want is we want to calculate the derivative at a point. So we should be able to go shift minus, all right, and we want the derivative with respect to t of v of t. Oh, actually, let's not do that. Let's go menu. Let's go calculus and do the derivative at a point. So our variable is t. We want to change that. The value is 3. All right, we want the first derivative, and we want to take it for v of t. That way, that just lets you evaluate it at the point right there, because that's what we want. And it is approximately -2.118. So that takes care of part A, 2.118. All right, now for part B, all right, let's take a look at part B. Now we want to find the position of the particle at t equals 3. So for the position, we need to know the initial position. Okay, so if I want to say S of t, we'll let S of t be position. And I'm just going to go ahead and write that up here just so I identify it. Let S of t equal position. So if I want to find S of t, that's going to equal S of 0 plus the integral from 0 to t of v of t, well, I guess it would be v of x dx. Now, that's what I'm looking for. So we know that the initial position, that was given as -5. So it's -5 plus. Now we're specifically looking for the position when time is 3. So we're going to integrate from 0 to 3 v of t dt. All right, and it would have been probably smarter to just do this, call this x, and just leave this v of t dt. All right, so now at that particular point, we can go back to our calculator, and we've got -5 plus, we can just go shift plus, and we're going to integrate from 0 to 3 of v of t dt. Hit enter, and we get approximately -1.760. So again, just a reminder, College Board is always going to want you to go to 3 decimal places. So that's going to take care of part B. All right, now for part C, it's asking us to evaluate the integral from 0 to 3.5 of v of t dt and evaluate the integral from 0 to 3.5 of the absolute value of v of t dt. Interpret the meaning of each integral in the context of this problem. So let's go ahead and start with the first integral. So if we integrate from 0 to 3.5 v of t dt, all right, we're going to put that in our calculator. So let's go shift plus. We're going from 0 to 3.5. Again, it's v of t dt. And you can kind of see by storing that v of t at the beginning has saved us from having to type it in over and over and over. So highly suggest you do that. All right, so what we get is about 2.844. You could put 843, but you do have to have 3 decimal places. So 2.844 is how I'm going to write that answer. So this is approximately 2.844. Now it does want to know what that means in the context of this problem. All right, so basically the integral of velocity, that gives you the displacement, how far the particle is from where you began. Okay, so what this would mean is basically at t equals 3.5 seconds, all right, and just to kind of go back and make sure, it actually didn't tell us time was in seconds, but so at t equals 3.5, the particle is 2.844 units, because again it doesn't give us specific units to the right of where the particle began. At t equals 0. All right, so that's what the integral, the displacement is, how far are you from where you began, and it's to the right because it's a positive value. Now the other part of this question was to evaluate the integral from 0 to 3.5 of the absolute value of velocity. So same idea, you're going to go to the calculator first. Let's go shift plus. We're going from 0 to 3.5 again. Whoops, 3.5. All right, now there are different ways to get to absolute value, but I think the easiest way, in my opinion, is just type in ABS. So if you do ABS, parentheses, and then V of t. dt. we're going to get the answer. And you can kind of see that it put the absolute value bars in there when we hit enter. And it's 3.737 in this case. So that is 3.737. Now, when you take the integral for the absolute value of velocity, that is the total distance. So we would interpret this as from t greater than or equal to 0 to less than or equal to 3.5, the particle traveled 3.737 units. Or let's maybe be more specific, traveled a total distance of 3.737 units. All right, and that's going to be part C. And then if we take a look at part D, it says, a second particle moves along the x-axis with position given by x of 2, x sub 2 of t equals t squared minus t for t greater than or equal to 0 and less than or equal to 3.5. It says, at what time are the two particles moving with the same velocity? Now, for us to answer part D, again, we're looking, when do they have the same velocity? So we are given the velocity of particle 1. That's what the t sine 0.4 t squared over t squared minus t plus 3 represents, v of t. You got to recognize that in part D, they're giving us the position function. So the first thing is, let's figure out what the velocity function is. So velocity of the second particle is going to be the derivative of position, so 2t minus 1. If we want to know when those velocities, or when they're moving in this, when they have the same velocity, those two velocities need to be equal, which means we're simply going to set up the equation of 2t minus 1 is equal to 10 sine of 0.4 t squared over t squared minus t plus 3. So we're going to set those equal and solve. So if we go to our calculator, we want to do algebra, we can solve, and we should be able to just kind of type in 2 times t minus 1 equals v of t, because we had already stored that. All right, and we're solving that with respect to the variable t. So we get an answer of 1.571. So we can go ahead and answer our question. The particles have the same velocity when t equals 1.571. Again, just remember 3 decimal places with College Board, unless it's an exact answer. But any approximation needs to be 3 decimals, rounded or truncated. All right, guys, that takes care of number 2, and that is the last calculator active question in this set of FRQs. So now, if we go ahead and we take a look at question number 3, all right, it's non-calculator, which it states clearly right there. All right, let's see what we got going on here. It says, the graph of the continuous function g, the derivative of function f, is shown above. The function g is a piecewise linear for x greater than or equal to -5 and less than 3, and g of x is equal to 2 times x minus 4 quantity squared for x greater than or equal to 3 and less than or equal to 6. All right, so there's some things that you definitely need to catch as you look at this. One, this is the graph of g, all right? Now, it also tells us that g is the derivative of f, and that's really important that you identify that. So g equals the derivative of f, because that relationship is definitely going to come into play. And then we have some information here. So A says if f of 1 equals 3, what is the value of f of negative 5? All right, so let's think about what we have here. We know the position of f of 1 is 3, and we want to know, or we know the value of f of 1 is 3. We want to know the value of f of negative 5, right? And g is equal to f prime. So basically, when we look at the graph, this graph is the derivative of f. So basically, what we would know, all right, and I'm going to kind of start A up here so we can use a little bit of room, is if we took the integral from negative 5 to 1 of g of x, if we took that integral, it's going to be essentially f of 1 minus f of negative 5. That's what that would represent. And then from there, what you kind of can find out is basically, because we know what f of 1 is, right? We want to know what f of 5 is, or f of negative 5. F of negative 5 is going to be f of 1, all right? And then it would essentially be minus the integral from negative 5 to 1 of g of x dx, if that makes sense. So in that case, we know that f of 1 is 3 minus. Now, when we want to calculate the integral from negative 5 to 1 of g of x, we're going to need to use area under the curve. So we've got this area right here, which is going to be the integral essentially from negative 5 to negative 1. And that's going to be a trapezoid. And it's below the x-axis, so it's going to be negative 1/2. And then let's see, the height is 3. And you've got base 1, which is 1, 2, 3, 4. Plus base 2, which is 1, 2, 3. And then to that, we're going to add, well, this is going to be 0. But we have to add this area right here, which is the area of that triangle, to get to 1. And when we add that, that's going to be 1/2 of 1 times 2. So again, this is not a calculator active problem, so let's see what we get. We've got 4 plus 3 is 7. 7 times 3 is 21. So that's going to be negative 21 halves, and then plus 1/2 of 1 times 2 is 1. So if we got a common denominator, that's going to be 6 halves minus, and then this would be negative 19 halves. So if we add those together, we get 25 halves, and f of negative 5 is 25 halves, or 12.5. All right, any questions? Well, I guess if you guys have questions, you want to look over it again. But, because g is the integral of f, because g is the derivative of f, in order for us to calculate, this, g of x is f prime. When we take the integral, we get f. All right, guys, looking at part B, evaluate the integral from 1 to 6 of g of x. So now, if we want to calculate the integral from 1 to 6 of g of x, let's take a look at that. So we got part B over here. So from 1 to 6, we are looking from here to here. All right, what is going to happen is what I would do is I would separate this here. And I would look at this as the integral. So when we do this, the integral from 1 to 6 of g of x dx, that is going to be the same thing as the integral from 1 to 3 of g of x dx, plus the integral from 3 to 6 of g of x dx. Now, the integral from 1 to 3, it's simple. It is this square right here. It's the area of that square. Okay, so that's going to be 2 times 2 plus. Now, from 3 to 6, though, we have this function that we're going to have to integrate. So we have 2 times x minus 4 quantity squared dx. Well, if we're going to go ahead and integrate that particular function, we need to, well, I would expand it first off. So this is going to become x squared minus 8x plus 16. And then when we multiply that by 2, we're going to get 2x squared minus 16x plus 32. That's then going to allow us to take the integral of that function. So this is going to be 4 plus, all right, this becomes 2/3 x cubed minus 8x squared plus 32x. And we need to evaluate that from 3 to 6. And I guess I could have left that 2 out in front, maybe made some calculations a little bit easier, but there it is. All right, so now we got to plug everything back into there to evaluate this integral. So this is going to be 4 plus. And then all of this, you've got 2/3 times 6 cubed minus 8 times 6 squared plus 32 times 6. And then from that, you're going to subtract 2/3 of 3 cubed minus 8 times 3 squared, oops, plus 32 times 3. Obviously, it would help to have a calculator here with us a little bit, but so let's just see what we got. 6 cubed, that's, let's see, 216. So 216 times 2 is that 432. So this is 432 over 3 minus, that's going to be 36 times 8. So 36 times 8, it's 288. And then 32 times 6, that's 192. All right, and then you've got, let's see, 3 cubed, that's 9, so that's going to be 18/3 minus 3 squared is 9, so 72 plus 96. All right, and then let's just kind of see what comes out of all of this. All right, so this is 432/3, that's 144. So you got negative 144 so this ends up being 48, and then minus, all right, this is 6. So 6 minus 72 plus 96. Let's see. Well, let's just do this. This is 102, and 102 minus 72 is 30. All right, I don't know why I put parentheses there, but you got 48 minus 30, so you got 4 plus 18. Let's see. All right, what did I screwed something up somewhere in here, I think. So if we're going to look at this, what did I do? Sorry, guys. I'm going to pause this real quick and try to find out where my mistake was. All right, guys. Sorry about that. I found my mistake. So just simple calculation errors. Right here, this is not 18/3. 3 cubed is 27. 27 times 2 is 54. So that's 54/3. So that's going to be 18 minus 72 and then plus 96. That's going to give us 42. And at that point, you've got 48. So 48 minus 42, that's 6. 4 plus 6 equals 10. So the integral from 1 to 6 of g of x dx equals 10. Sorry about that. Just be careful. And again, I think I would have made my life a little bit easier had I just left this 2 and pulled it in front instead of multiplying it through. just don't always see everything at the very beginning. All right, so now if we take a look at part C, it says for x greater than -5 and less than 6, on what open intervals, if any, is the graph of f both increasing and concave up? Give a reason for your answer. All right, when you take a look at this, what becomes extremely important for this problem is understanding this relationship right here, that the graph of g, okay, which is the derivative of f, is what we're looking at. All right, so here's what we're going to say for part C. It does say give a reason, so I'm going to start with the reason. All right, f is increasing and concave up when, all right, well, the function's going to increase when the derivative is positive, okay? So f is increasing and concave up when f prime is greater than 0 and f prime is increasing. Because if f prime is increasing, then that means that the second derivative is positive. So we're looking for when is the derivative positive and increasing on that interval, okay? So we can say this occurs. All right, so we want positive and increasing. Well, we're negative, we're 0. All right, so we are positive and increasing from 0 to 1, okay? So x is greater than 0, less than 1, all right? Then we're positive, but it's constant. We're positive and decreasing, and then we're positive and increasing again from 4 to 6. All right, and that is what we are looking for. Because in order for the function, or f, to be increasing, the derivative needs to be positive. In order for it to be concave up, the second derivative needs to be positive. So f prime is increasing. Basically, what this is the same thing as, sorry, I should probably add this in as part of my explanation. F double prime is greater than 0. All right, and then for part D, it says find the x-coordinate of each point of inflection. Give a reason for your answer. So again, with a point of inflection, I'm going to go ahead and give my reasoning first. F has a point of inflection when f double prime equals 0 or is undefined and changes signs. All right, that's typically what we're going to use, what we're going to look for with a point of inflection. Now, the graph that we're given is not f double prime, it's f prime. Okay, so you can also, so f has a point of inflection when f double prime is 0 or undefined and changes signs. Okay, which happens at extrema of f prime, okay? So any relative extrema of f prime is going to be a point of inflection. So as we look at the graph, the only relative extrema that we have is this point right here, this relative minimum, when x equals 4, okay? So x equals 4 is the only extrema of f prime, so it is the only point of inflection for f. Oops. All right, guys, hopefully you found the videos helpful. Watch them as much as you need to, and just really become familiar with these problems, and I will see you next time.